So there's kind of two very closely related sections. One of them is in chapter 1. It's the next section we're supposed to cover, which is infinite limits. And then one of them is in chapter 5, which is limits at infinity. I'm sorry, in chapter 3, not chapter 5. So infinite limits and limits at infinity are completely different things. But they sound similar and they are related. Basically, an infinite limit is like a vertical asymptote in your graph. And a limit at infinity is like a horizontal asymptote in your graph. So since they go together in that aspect, in that way of thinking, I wanted to cover them at the same time-ish, which is why I moved up to 3.5. So, but let's just go through. Start with 1.5. See how far we get. Oh, good, okay. So there's really only one definition, one thing to discuss here. I mean, it gets confusing, but there's only one main concept, and that's what it means to have an infinite limit. So if, as x approaches c from both sides, f of x increases without bound, so your y values increase without stopping. We say the limit as x goes to c of f of x equals, so this is the usual limit notation. Since we're increasing without bound, since f of x is getting bigger and bigger and bigger and bigger and bigger, what do you think this limit is going to equal? Infinity. This is kind of our new concept, our new idea. Before, if we didn't approach a single finite y value, we said the limit doesn't exist. But now what we're saying, well, actually, if our function keeps going up forever on both sides of c, instead of saying does not exist, we're going to say infinity. So for example, just a quick example so you understand what I'm trying to get at here. 1 over x squared, which looks like a volcano I learned, would have an infinite limit as x goes to 0. This guy is f of x equals 1 over x squared. And so the limit as x goes to 0, 1 over x squared equals infinity. Because on both sides, right, as you approach 0 on both sides, 0, 0, your function increases without bound. Keeps going up forever and ever and ever and ever. Now, there's a couple of variations on this. For example, I could change this definition to say, if as x approaches c from both sides, f of x decreases without bound. Right? Instead of f of x increases, I could say decreases. What do you think that changes? Then instead of going to positive infinity, you go to negative infinity. Right? So you would write the limit as x goes to c of f of x. So if you change increases to decreases, your limit becomes negative. The other thing I could do over here is instead of saying from both sides, I could say from the left. I could spell from left. Or I could say from right. do you think that changes in my result here? The plus or minus on the c, right? If as x approaches c from the left, f of x increases without bound, then you would say something like the limit as x goes to c from a minus side of f of x equals infinity. And then, or from the right, then you would get the limit as x goes to c on the positive side of f of x equals infinity. So that's what 1.5 is about. Determining when you actually have an infinite limit, right? Determining when you can put infinity as your answer for a limit. And it's really, at this point, there's kind of one simple intuition that you should be thinking through. If you plug in your x value and you get a constant over 0, so limits of the form constant, so actually some non-zero constant. Limits of the form c over 0 for some non-zero constant over 0 approach plus or minus infinity. So for example, if I were to try and plug 0 in here, I would get 1 over 0. Since I have a non-zero constant over 0, I know that I'm going to go to plus or minus infinity. So this constant has to be a non-zero. If you get 0 over 0, that's indeterminate. Then you got to factor or rationalize or do whatever trick you have up your sleeve. But if you get something that's not 0 over 0, then it's going to go to plus or minus infinity. How do you determine whether it's positive infinity or negative infinity?
The graph.
Either graph it, or, any other suggestions? Plug in a point. Right? Maybe test a couple of values, one on each side if it's a double-sided limit. So to determine whether you're going to positive or negative infinity, you want to test points or graph. Depends on how easy it is. I mean, if it's a simple graph like 1 over x squared, you're probably better off just graphing. But if it's a complicated graph, you might just want to test points. Okay. Let's do some examples. By the way, before I erase this, what if instead of 1 over x squared, I'd given you 1 over x?
But they don't go the same way.
Yeah, so if I wanted you to calculate, let me do it right here, the limit as x goes to 0 of 1 over x. Yeah, this overall limit, though, the one that doesn't have a plus or a minus, this does not exist still.
Need the plus and minus. Plus minus.
Right, because no matter what, you're not going to increase without bound or decrease without bound. You're going to switch. You're going to do both. Right? On this side, you're going to decrease. On this side, you're going to increase. So on one side, you're going to positive infinity. On the other side, you're going to negative. But if you, like you guys are thinking, if you put in a plus or a minus down here, then you do have a limit. So what if I did a little plus?
Infinity.
So if I go to 0 from the positive side of 1 over x, then I'm looking at the right. Then I shoot off to positive infinity. Similarly, if I go from the negative side, what would I go to?
Negative infinity.
Right. Positive side of 0. 0 plus. Go up here. This is the negative side of 0. Go down. All right, so let's do some examples. Chinese limit. Let's do the limit as x goes to 5 of 1 over x minus 5. So when you plug in, so we're trying to calculate this limit, and one of the things we learned to do is just plug it in and see if we get 0 over 0, or see if it makes sense. So the first thing I would definitely encourage is plug it in. In this case, we get 1 over 0 if we plug it in. As soon as you get a non-zero constant, any constant that's not 0, over 0, you're thinking infinity. Right? This should be hopefully infinity. But you have to make sure that they're going to the same infinity on both sides, because this is a double-sided limit. Right? This is both sides. It's not a plus or a minus. It's not. How do you know that?
4.9 would be negative, 5.1 would be positive.
Yeah, so one way to check it real quick is just plug in a value on each side of 5. 4.9, 5.1. And then just figure out if it's positive or negative. If you plug in 4.9, you get a negative number, because 4.9 minus 5 is negative. And if you plug in 5.1, you get a positive number, because 5.1 minus 5 is positive. So I know I'm going to infinity on either side, but because one side I get a negative and one side I get a positive, I'm approaching different infinities on in this situation again. So I would write does not exist. In order for the overall limit to exist, you have to approach the same thing from both sides. And this clearly is approaching different infinities, because one's negative and one's positive. What if I fixed it up like this? Limit as x goes to 5 from the negative of 1 over x minus 5. Right, so now it's still 1 over 0 if I try to plug in, so I'm looking for some sort of infinity, but I only have to check one side for my sign. I only have to check the left side, the numbers that are less than 5. So when I plug in my extra value, I will only plug in 4.9 and see that it's negative. So this will equal negative infinity, because there's no other side to match up with. What about limit as x goes to 5 of 1 over x minus 5 squared?
Infinity.
Yeah, so when you plug this in, it becomes 1 over 0. Right, 1 on top, 0 on the bottom. That's telling you you're looking for some sort of infinity. Now you just have to check and make sure that the signs, that they're both going to the same infinity. But they are both going to the same infinity because of this square, right? Whether you do 4.9 or you do 5.1, whether you go left or right, you're going to square the result, so you're going to get positive either way. So this is going to equal. What about the limit as, well, let's do x goes to 1 of x squared minus x over x squared minus 1. What do you get when you plug 1 in here? 0 over 0, not c over 0, not a non-zero constant over 0. 0 over 0. 0 over 0 is indeterminate. This may or may not be infinity, I have no idea yet. So what might you do to help you simplify this? Factor. Right? When you get 0 over 0, you've got to do a little more work first. So limit as x goes to 1 of x times x minus 1. Right? And x comes out on top. Difference of squares on bottom. X minus 1 gives you a whole. So really, when you just have to worry about the limit as x goes to 1 of x over x plus 1, which when you plug in is 1/2, right? So what I'm trying to remind you of here is, if you have 0 over 0, you're not necessarily going to get infinity. That's back to the old methods. You could still get infinity if you have 0 over 0. Question? Oh, over
No,
here?
I mean, that's eventually ends up to be 1.
Yeah, you set this equal to 0 and move it over, yeah. Let me give you a similar example. Question? No. What about limit as x goes to 1 from the negative of x squared minus 1 over x squared minus 2x plus 1. If you plug 1 in, just to check and see what happens, you get 0 on top, 1 minus 2 plus 1, 0 on bottom. So it's not necessarily an infinite limit at this point, it's an indeterminate.
So we'll make it x minus 1 times x plus 1 on top, and then
Exactly.
x minus 1 squared on the bottom.
All right, so factor this bad boy x minus 1, x plus 1 on top. This guy you have to reverse FOIL or guessing check or whatever you do. This is x minus 1 minus 1, right? Two things that multiply to 1 without to -2. Keep your limit. Now this guy reduces away, which means again we had a hole at x equals 1. Well, you might think that. Unfortunately, there's not, it's not actually a hole here because you still have an x minus 1 factor.
You have a constant over 0?
Yeah, so when you try to plug in now, on top, if you plug in 1, you get 2, but on bottom, if you plug in 1, you get 0. So you have a non-zero constant over 0. This is going to go to some sort of infinity. Since it's a one-sided limit, we know it'll definitely go to one kind of infinity. And how do you figure out what infinity? Plug in.
Negative infinity.
Yeah. All right, you want to plug in numbers on the left of 1, x, f of x. So I would plug in something like 0.9. If you put 0.9 underneath here, 0.9 minus 1 is negative, 0.9 plus 1 is positive. So the result is negative. So this guy's going to negative infinity. limit x goes to pi over 2 from the negative side of tan x. So this one's perhaps a little different, maybe, but at the same time not really. One way to do this, one way to think about this is to remember that tangent x is sine x over cosine x. Limit that way. Then it mirrors this format here. And you can plug something in and see what you get.
1 over 0.
Yeah, if you plug pi over 2 in, here's your unit circle, here's pi over 2, here's 0, 1. So sine at pi over 2 will be 1, cosine at pi over 2 will be 0. So this is 1 over 0. It's telling you infinity. And the whole trick is to just figure out the SIGN.
Positive.
So you have x, tan x, or your function. You plug in something slightly less than pi over 2. Now, this is a little tricky, right? Because what's slightly less than pi over 2? Well, I don't know, pi over 2 minus 0.001, right? So you could go a little bit, you could do something like pi over 4 or pi over 3. You can do something more than slightly less. Sine and cosine are both positive there. Right? And pi over 4, sine and cosine are both positive, so this will be positive.
The graph.
The other way to do it is with the graph, absolutely. If you have a good image for the tangent x graph in your head, it's just a snake, and it's got asymptotes at pi over 2 and negative pi over 2. Well, it's got a bunch of asymptotes, but those are the first few. So this tells you to the left of pi over 2, tangent is going up to infinity. So either way, positive infinity. If you got a calculator, you could plug in pi over 4, pi over 3, or you could either type pi over 2 minus 0.01 and get that answer and plug it into sine and cosine. But if you don't have a calculator, you're going to want to pick something that you know, like pi over 4, pi over 3, something slightly less than pi over 2. Or remember the graph.
So x going towards negative pi over 2.
Well, going towards pi over 2 from the
Yeah,
from
I
the
know.
negative
I was
side,
just saying,
uh-huh.
if there was a different one, like
oh, so negative pi over 2, yeah.
going towards the left, it would be positive also.
Gotcha. So you're asking what the
For the other
limit
side of that graph.
of negative pi over 2, from the left still, of tan is, I gotcha. So this, you're saying this part over here. Right here?
Yeah.
That would be positive infinity. So this limit would be positive infinity. And if you approach negative pi over 2 from the left, you're shooting up to infinity. This might get you in trouble with trig functions. Okay, so be careful with this, because for example, if you're trying to figure out what to plug in around negative pi over 2, you actually have to pick an angle that's more negative than negative pi over 2. You have to pick something over here. So you would have to pick like negative 3 pi over 4. And that would give you sine and cosine are both negative, so you get positive. So this is a little trickier for trig functions using a table. Certainly the graph will always give it to you. Let's do another trig function. Limit as x goes to 5 pi over 2 from the positive side of secant x. So I would encourage you to think of this as 1 over cos x. Realize when you plug in 5 pi over 2 to cos x, what do you get? 0. It's 5 pi over 2. Here's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. It lands right back here. So cosine 0. So this will be 1 over 0. So some sort of infinity, but we need to focus on the positive side. Yeah, so either you remember the graph or you think of something that's bigger than 5 pi over 2. Slightly bigger than 5 pi. Is it positive in that?
Yeah, really graph cosine, right at pi over 2 would go up the asymptote.
It's negative.
Yeah, I think it's negative.
It's headed downward at that point.
So
If you graph cosine,
Oh, I will.
you use above it.
I will. So either you could plug in something over here, which is telling me since cosine is negative, that I should get a negative, since cosine is negative in the second quadrant. Or you can graph the cosine function, which starts at 1. Let's see, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. So the cosine function is going to start up at 1. Right, cosine starts at a max, 0, min, 0, max, 0, min. And so your secant function, if you remember the way secant works, since it's 1 over cosine, these guys become asymptotes. All the zeros become asymptotes. And so these bumps get flipped up. Yeah, so since we're coming from the positive side, we actually want to focus on this portion over here, the positive side of 5 pi over 2. And the positive side of 5 pi over 2 is actually putting us down to negative infinity. And so the other way to think of that, like I said, if you plug in something a little bit bigger than 5 pi over 2, you're going to be a little bit more to the left, so that's going to put you in the second quadrant. So it's clear from that, because cosine is negative in the second quadrant, that it should be negative infinity. Either way.
That was a good example, though.
That one's tricky. Not good to look at anyway. about, oh, I don't remember what letter I was on. You know what letter I was on? G? Was that
Although
G?
now it's
H.
H.
Um, limit as x goes to 0 of x cosecant x.
Zero.
So you gotta be careful here. What happens?
Infinity, yeah, yeah.
What happens when you plug in 0?
Cosecant is 1 over sine x.
Yeah, let's rewrite it.
1 over 2.
Let's rewrite it as a fraction. This will be x times 1 over sine x. Or
X over sine
x over sine x. You multiply those out. Which means if you plug in 0, actually you get 0 on top and 0 on bottom. So that's indeterminate. Which should set off alarm bells in your head, hopefully. Because when you're indeterminate form, you have to find another way to work with this, right? It's not necessarily going to be infinity. So what's the trick for this?
It's just one.
It's just 1. Why is this 1?
This is
It's our special limit, right? We have 2 special trig forms. Well, it's the reciprocal of our special trig form. Right? Remember, we had the limit as theta goes to 0 of sine x over x equals 1. And the limit as theta goes to 0 of 1 minus cos x over x. So this guy is the reciprocal of this guy. So if he goes to 1, he's going to go to the reciprocal of 1. And the reciprocal of 1. Now compare and contrast. What if I gave you limit as x goes to pi of x cosecant x? Let's do from a side this time. From the positive side. So I've changed this from 0. The function's the same, but I want to see what happens around pi instead of 0.
Pi over 0.
Yeah, so now, when I rewrite it in my fraction form, limit as x goes to pi from the positive of x over sine x. When you plug in pi to the sine function, you get 0, because pi is way over here. So maybe 1, 0, so sine 0. So you get 0 on the bottom, but when you plug in pi to the top, you get pi. So a non-zero constant over 0, now we're expecting some sort of infinity. And so the whole trick becomes figuring out what the signs are on the bottom. Now I don't actually know what the graph of x over sine x looks like.
Can we push it?
What's that?
Can we push the limit for limit of as x goes to pi of x, and then limit of cosecant x, and multiply it?
Yeah, you could try that. Yeah, that's bad math, right? Because what? Do you know why that's bad math?
Not included.
I'll let you know. I'll let you know right after I write it. You cannot. The only time you cannot distribute the limit is if one of the limits doesn't exist. Okay, and since this guy's infinity, we haven't talked about what happens when one of the limits is infinity, whether you can distribute it or not, because then you'd have to say, well, what's pi times infinity? So that's turns out pi times infinity will always give you infinity. Right? So it's okay, but we haven't discussed it yet.
Okay.
The sort of the hypotheses for being able to distribute the limit are that both of the limits are finite.
Okay.
But you can figure out what's the sign of sine for values that are slightly more positive than pi, for values down here. Like at 5 pi over 4, down in the third quadrant, what's sign, positive or negative? Negative. Everything's negative in the third quadrant, sine and cosine. Right, so if you pick something in the third quadrant, something slightly more than pi, you'll get a negative result at the bottom, but you'll get a positive result at the top still, so the overall result. But like you said, you can also use the cosecant graph. And if this totally made no sense to you, you can also think, okay, well, let me graph cosecant. Right? Cosecant looks like sine, except inverted. So here's my sine graph. Here's where my asymptote's going to end up for cosecant. This guy's pi. So bigger than pi means cosecant's going down to negative infinity. This extra x times negative infinity is not going to make it positive all of a sudden. Right? Pi times negative infinity is still going to be negative infinity.
That's what I was thinking, just increase the amplitude of the sine, right?
Right, well, yeah. I honestly don't know what this graph looks like. I mean, the x is gonna make it stretch it out in a proportionate way, right? As x gets bigger, it stretches it out more. But it's certainly not going to change the asymptotes. It's not going to change the sign. S-I-G-N. Okay, that's kind of that's infinite limits. It gets a little tricky with the trig functions, right? With the polynomial, with the rational functions, it's not quite as bad, hopefully. Let me talk about, for 20 minutes, talk about 3.5. So 1.5, which is what we just finished, was about infinite limits. And it focused on the form some constant over 0. Non-zero constant over 0. 3.5, we'll start now, focuses on limits at infinity. And kind of just like 1.5, there's really one major definition, and then you just go in and make sure you know how to deal with that definition. So limits at infinity, a limit at infinity. Looks like this. So this is what we'll conquer this. Done, check, A+, owned it. So, for limits at infinity, if as x increases forever without bound, f of x approaches a single finite value, gets arbitrarily close to a single finite value. Then we say, let's call the value L. Then we say goes to infinity. So because x is increasing without bound, we're going to say x is going to positive infinity. So the limit as x goes to positive infinity of f of x equals L. If this is true. If as x increases, f of x approaches L. Give me a quick baby example. What do you know the limit of as x goes to infinity? 1 over x. Yes, absolutely. Limit as x goes to infinity of 1 over x. If you want to just look at the graph, that might be the easiest way. Here's your function. As x increases without bound, means we're going this way. X is getting bigger and bigger and bigger. X is moving toward positive infinity. That's what x increases without bound means. F of x approaches a single finite value, L. So then, as x goes to infinity, I need to figure out what my y values are approaching.
0.
In this case, it's 0. So because my y values are approaching 0 way out here, they're getting super close to the x-axis, I will say this limit equals 0.
Oh, that's on both.
Yeah, so here I said if x increases without bound, this is my limit, right? But I could say the same thing for decreases without bound. If you allow your x values to decrease without bound, what do you think changes here?
Negative infinity.
You go to negative infinity. So if you change this increase to decrease, the result says the limit as x goes to negative infinity of f of x. That's L. It's possible too. So that's what happens over here, right? We can also calculate the limit as x goes to negative infinity of 1 over x. Because x is going to negative infinity, x is decreasing without bound, you're focusing on the left.
Still going to 0.
Still going to 0, right? As x goes to negative infinity, if you look at where your function values, your y values are going, they're hugging up on that x-axis again. So you're getting closer, y is getting closer to 0. Does it make sense to do something like this? Infinity from the positive side.
No, because we're saying increase or decrease.
Yeah, I mean, you can't be on this side of infinity. It doesn't mean anything. Okay, so there's no left or right for limits at infinity. There's just infinity or negative infinity. It's possible that you can say, it's possible that you can have a limit as x goes to infinity of f of x equal infinity. So how would this happen?
X squared.
Right, so this is saying as x increases without bound, y increases without bound. So, yeah, anything that goes up and up forever. Right, so x squared. This limit as x goes to infinity will be infinity. Because as x increases without bound,
So does
y
y.
increases without bound.
Like absolute value.
What's that?
Like absolute value.
Absolute value of x, yes, absolutely. So if you do not go to a single finite L value, and you just increase forever, then then the limit will be equal to infinity. Or negative infinity if you go decrease forever. Alright, so let's do some. Oh, we'll do examples. Let me give you the kind of the intuition here, what you should be looking for. you run into for these limits at infinity, here's your possible forms. You could get something like a constant over infinity, a non-zero constant again. Not that 0 over infinity really matters. 0 over infinity not going to matter. So a constant over infinity, what do you think this goes to and why? If you take 2 and you divide it by 1,000,000, what do you get? Practically 0. Right? If you take $2 divided among 1,000,000 people, each person's going to get nothing. Right? So a constant over infinity, a finite value over an infinite value, will go to 0. What about the other way around? Infinite value over a constant.
Infinite.
This goes to infinity. If you take $1,000,000, divide it among 2 people, you guys are rolling pretty deep, right? So as the top gets bigger, if the bottom stays constant, then you're going to infinity. Now, the last kind of annoying form, infinity over infinity. This is another indeterminate form. You can't say anything without more analysis. If these are both growing without bound, then I don't know. I don't know. It depends on which one grows faster, what this goes to. Okay? So this is an indeterminate form. And my advice in this case, for now, is going to be to divide by the highest power. I'll show you what that means. Okay, so we're switching it up a little bit now. Right, when I do my limits now, all my limits are going to have x going to infinity. Right, and we want to figure out what y is going to. Before, x was going to 2 or 3 or a constant. But now x is going to be going to infinity. So let me do some examples here. So find each limit. So if I give you something like the limit as x goes to infinity of, I don't know, let's do 5 over x squared plus 3x plus 7. What are you going to tell me? 0. Why? Yeah, if you think about plugging in infinity, right? You can't actually plug it in because it's not a number. But if you can think about plugging in infinity here, you're going to square a really big number. You're going to add to that a really big number times 3. And you're going to add 7, which is really important. So the bottom is going to end up being huge. So you're in the form constant over infinity, which we know equals. Now, it's hard to get one of these forms immediately. Right? The only way you can get a constant over infinity immediately when you're taking x to infinity is if the top is constant, or the bottom is constant. Right? As soon as you make the top or bottom not constant, you have a problem. So for example, I could give you the limit as x goes to infinity of 5x squared plus 1 over 10x squared minus 3x plus 7.
Infinity 1/2.
Right? As soon as you put an x on top or bottom, if x is going to infinity, the top or bottom are both going to go to infinity.
Oh, 10x squared. Still
So-
the bottom
so-
is smaller. I mean, top smaller.
So this, when you evaluate it, is infinity over infinity. Now, if you remember things from your pre-calculus class and you understand that this is like a horizontal asymptote, you'll know that this is going to 1/2. But this isn't pre-calculus, this is calculus. So you're going to give me a calculus reason why this is going to 1/2. So this is where this idea of dividing by the highest power helps you out a little bit. Right, so when you get this infinity over infinity, one way to see what's going on is to say, all right, well, x squared is my highest power of everything. So to try and simplify this, to try and make it more clear, I'm going to divide everything by x squared. That shouldn't change my function because I'm doing it to everything, top and bottom. Right, if you do the same thing if you divide the same thing on top and bottom, it will not change your function. So I'm going to write this as 5x squared divided by x squared plus 1 divided by x squared over, and I'm going to take each of these and divide them by x squared. So effectively, I've divided the top by x squared and I've divided the bottom by x squared. And it looks like it's hopeless and there's no way we can ever figure this out. But actually, it's not too bad. Some things are nice. 5x squared over x squared, what's that equal to? 5. 1 over x squared, I can't simplify, so I'll leave it. 10x squared over x squared. Negative 3x over x squared. 7 over x squared. Now, each of these guys is of the form constant over infinity when you plug in now. Right? This is 5, this is 10, but this guy, when you plug in infinity, is constant over infinity. This guy is constant over infinity, constant over infinity. So what do each one of these go to?
0.
0.
It's 1 over 2.
This goes to 0, this goes to 0, this goes to 0. And that's why the limit is 1/2. Because you get a bunch of these. So this, like I was kind of saying before, when it's a rational function, when it's something you've dealt with before, I understand how you can see that the limit is going to be the ratio of the leading coefficients. But when I start throwing roots in there, or trig functions, it becomes a little more complicated, and you definitely want to have this strategy down. Okay, dividing by the highest power. All right, we'll get there. Not today. Let's see, I'll do one more and I'll let you go. So, I don't know if you're ready for that one. All right, I'll give you one. can't take the square root across a plus sign. Well, that's not what you're doing. I know that's not what you're doing.
Well, like I was thinking, like if you take the bottom, it'd be basically the 1 would be negligible.
Right. So your argument is that the 1 is negligible, and then you can take the square root, and that's okay.
Yeah.
But that's touchy feely.
We should multiply
That's not
both
math.
denominator and both of them like 1 multiply time square root of x.
Yes. So what you're saying is correct. It's just not math. It's a little. It's a little too.
Gambling.
It's a little too gut feeling-y and not enough. You know, actual math. So what you really want to do here is think, like you're saying, effectively the highest power is 1, right? Because the square root of x squared is x. Well, we'll get to that in a second. But we think the square root of x squared is x. So effectively, you want to divide both top and bottom by x here, right? Because it is definitely an indeterminate form, right? When you plug in infinity, you get infinity on top, and you get infinity squared, which is still going to be infinity when you square root it again. So it's definitely an indeterminate form. The way to handle this is to multiply by 1 over x on top and bottom. On the top, that's dividing by x, so this will just be x over x. On the bottom, you have to get this x into the root. So to get the x into the root, what is this x going to become when it goes into the root? X squared. Right? So actually what you have here is 1 over root x squared. You rewrite the x as root x squared, and then it can move into the root. So this will be 1 on top, because those cancel. On the bottom, it'll be root x squared plus 1 over x squared. In order for the x to move into the root, it has to become x squared. So now you can simplify this as limit as x goes to infinity. This is 1 over square root divided out into both. 1 plus 1 over x squared. This guy goes to 0 because it's a constant over infinity. That was our one rule. One of our basic rules for this section. So it is indeed 1 over root 1. Now, you may think I'm being anal, and I am a little. But let me leave you on something. I'll talk about this again next time, because this is very tricky. But let me leave you with something you might not believe. Maybe. This function is actually cool because if you go the other way, if you go to negative infinity instead of positive infinity, the limit changes. This is actually equal to negative. So I'll let you think about why that's true. And we'll talk about it next time after the quiz. Okay? So when you get here on Wednesday, we'll have a quiz over what? 1314?
Yes.
And then we'll finish up everything about infinite limits. Talk about some asymptotes too. Infinite limits and limits.